Hello, my name is Kohei Hanaoka. Today, I will talk about the topic entitled Development of 3D printed structure that visualizes bending and compression deformations for soft-bodied robots. The right side movie shows our proposed method, which can sense the bending and compression deformations simultaneously. Here is the outline of this presentation. First of all, I will show you the demonstration of the proposed method. Then I will explain the design and algorithm. After that, I will show the experiment and its results and discussion. Next, let me show you two applications. So, I will compare our method with others. Finally, I will conclude the presentation and talk about the future work a little bit. First of all, let me show you the demonstration. The proposed method includes 3D printed structure shown as the side view's bottom, RGB camera on the above, and the image processing algorithm. The top view is a captured movie from the RGB camera. From the movie, the proposed image processing algorithm can measure the deformation of the structure, as can be seen in the right bottom estimated shape. Let me explain how it works. As you can see the photo, the structure prism's part is painted with multiple colors. AR markers attached on the edges. The stiffness adjustable structure consists of a wave structure. We design the prisms in ways that the area ratio of the visible colors changes depending on angle. So using the equations, the tilted angle, alpha, can be calculated. More precisely, alpha is the angle between camera's direction and the normal of the 3D shape. To define the surface, we need theta, which requires beta 2. How can we calculate beta? Firstly, let's get M1 from the algo library in OpenCV. Secondly, we get the positions of the AR markers and the colored parts on the image sensor. At this point, the two triangles, orange and green, are similar, so the following equations is valid. As a result, beta is obtained, so theta can be determined. Let's estimate the shape. The colored part of the left side is on the red dot line. There are 6 of these parts. Since this method is for elastic materials, we assumed that the connection points on the image sensor would be the midpoints of each colored parts. The start point of the drawing shape is M1 obtained from the algo library, and the left and right side angles use the same angles of the marker as well. By connecting them, the shape is obtained. Now, let me explain the experimental setup. We used a cheap web camera, a logical C615N, whose resolution is 640 times 480 pixels. To verify the proposed method, we measure the position of X4Z4 and compare the position acquired from motion capture 5 OptiTrack Prime 13. Here is the result. Mean error of x-coordinate left graph is 0.95 mm, and mean error of z-coordinate right graph is 1.66 mm. We assume small torsions, such as torsion, that cannot be detected by method causes the error. Now on, I'd like to show you two applications. This is the first one, sensing motion of a caterpillar-like robot. We attach a 3D printed structure to caterpillar-like robot, like this movie. Then we measure motion with the proposed algorithm. This is how the proposed method can acquire the motion. As you can see the bottom right movie, the motion of the body was successfully measured by the proposed method. Another application is making a tactile sensor. We attach a 3D printed structure on knit materials. The knit is then attached to a hollow box to make a tactile sensor that detects deformation of the knit part. Here is how it works. As can be seen in the right bottom movie, the estimated shape successfully regenerates the gentle curve of the corners. Here is another object. As can be seen in the right bottom movie, the estimated shape successfully regenerates the curve of the sharper angular corners. The following is a comparison between our method and others. There are several ways to measure motion of soft-bodied robots. Most famous and popular one is motion capture, whose advantage is high accurate sensing of the deformation distributions, but the system is expensive with its issues. Stress sensor is another way to sense soft-bodied robots' deformation. The advantage is the ability to be embedded in the robot, and no extra device is needed outside. On the other hand, the way requires many wires for multi-modal measurement. RGBD camera is easy and low-cost shape measurement, but this requires computational cost when you want to sense the continuum deformations of soft-bodied robots. In terms of tracking point clouds with cameras, the famous one is Gale sight. The pros is high sensitivity in measuring small deformations, and the con is difficulty to measure large deformation. Compared with the related works, our proposed method can measure continuum bending and compression deformations, I mean multi-modal deformation, with single chip CCD camera. The issue is that the measurable area is limited and precision. Finally, I conclude the presentation. As summary, this study proposes a new soft robot shape measurement algorithm using a 3D printed structure with multicolored patterns and image processing. The proposed method can measure the bending and expansion contraction deformation distribution of a beam using a cheap commercially available CCD camera. We also demonstrate two applications to use the proposed methods: motion measurement of a caterpillar-like robot, soft robots, and a tactile sensor. As future work, we will try to measure 3D deformations of a surface and improve image processing algorithm high accuracy, and design feedback control for soft-bodied robots. Finally, this research was supported by following grants. Thank you for listening.